Welcome, I'm Elizabeth Irvin from the University of Mississippi, and we're going to talk about index combination for damage localization using genetic algorithm. The American Society of Civil Engineers says America has a D plus in their overall infrastructure and a C plus in bridges. This means that about 9% of bridges are structurally deficient. The best way that we have to inspect them is through non-destructive techniques, the mainly visual inspection. Visual inspection takes a lot of time and expense. We then also have a subjective measure that comes out of it, condition states from good to severe. So we'd like to have something that's more objective. Structural health monitoring may be a great choice for the Golden Gate Bridge, but not a local overpass. So for this purpose, structural health evaluation may be a better choice. Here you take two periodic inspections, perhaps 2 years apart, perhaps 10 years apart. The resolution is based on the number of sensors you have, and the excitation can be asynchronous because it's based on a modal method. And the data is then mined by the genetic algorithm to locate the damage as the difference between the two data sets. So the concept is first you take the measurements, and then you perform modal analysis, identifying some important modal properties. You put those and use those to calculate some damage sensitive features, which are mode, shape, flexibility, curvature, and strain energy. Apply mathematical methods such as summation, difference, probability, density functions, and come out with some damage indices. Now let's talk about some of those damage indices. There are 24 that we've come up with. The ones with the blue cross are from literature, and the other ones are just variations on those. And the idea is that we have 24 three-dimensional damage indicators. So we have an X, Y, and Z for each of those. How do we pick one damage indicator that works? Well, the genetic algorithm will decide for a specific structure which damage indicator or indicators works the best. That way we don't guess and assume one is going to fit all structures. So the way this works is you start with a target vector of where you suspect that the damage would be. We're going to discuss the unbiased, where there is no target vector. There is only all zeros or all ones because we're talking binary. And then we look at a weighted density, a weighted function for the damage index, which is the P. We calculate the error, which is the prediction versus the target vector, and we end up with an objective function that is the square root sum of the squares of that function. The output tells us alpha. The alpha is the best fit, which is the weight coefficient for each of the damage indices. 100% meaning that fit the damage perfectly, and 0% meaning it didn't fit the damage at all. So the evaluation parameters are first fitness value. That's the numerical accuracy, and it's based upon the number of sensors. So if we have a really high fitness value, that's telling us we've got a lot of error in the system, and so we need some more sensors. And the absolute difference tells us if we have good detection, which is a good difference between the undamaged locations and the damaged locations. So we performed a finite element analysis on a damaged frame, and this is one we performed experiments on also later. And there are 52 nodes, 12 beams, and 4 columns, 4 continuous columns. And of the 12 beams, the one beam on the second floor was then damaged. And we induced damage in Young's modulus, saying that the material had softened. And we reduced it by 40%, which is a significant amount. The result with a biased target vector, the target vector on the left shows that the bias was we knew where the damage was. That means the visual inspection gave us identifiers on that beam. The end result is the optimized damage detection shows in the middle of that structure is a 94% reading and 61% on either edge. And if you notice all the other structures in green, which is a lower percentage, less than 7% is our noise. So what it's saying is all of those points have a 7% or less possibility of being damaged, but this one location has a 94% possibility of being damaged. So that would tell the inspector where to go look, and it would give him an idea of how bad it is. In the unbiased target vector, what we have are either all zeros on the left or all ones on the right. If you have all zeros, you'll notice that the damaged location has a 100% damage. It means 100% difference. I mean, that means something's happening there, definitely. And we also have a 60% on either side. If you notice, though, there is more scatter on the other locations, including an 89% at the base, because there's nobody telling it where the damage might be. So this inspector might have a few more places to look. However, if he had all ones for the target vector, which means 100% damage everywhere, he's going to have this result, which we do not like because it has a lot of false positives. We performed a parameter study on the reduction in Young's modulus, anything from reduced by 10 to the minus 8 to reduced by 99%. And each of these were modeled, the modes were matched, and if you'll notice, the decrease as damage increases, the number of modes that we were able to match decreases. And that makes sense because the two structures are becoming more and more different. The two data sets are becoming more and more different. The results of the severity analysis are shown here. The horizontal threshold is 36%. Any absolute difference above that shows a good difference between the measurements. If you look at the vertical threshold, it is 2.3% the fitness value. If anything lower than that average fitness value, that tells us that we have good numerical accuracy. So if you'll notice in the red bricks, red blocks, that you have a reduction in E of 98%, which means the beam is almost not there. And what we see is a 98% damage in the center with 83% on either side. We see that decrease as we go to a damage reduction of 30%, which would leave an E of 70%. And we still see that the damage is detectable, but with a 92% and then 70 on either side. The undetectable regions in the red section that we call region 4, notice that we have all green here, which means less than 30% for 1 times 10 to the minus 6th. And so what we see is that we're not able to locate any of that. It was interesting that the trend was linear for these. And so with this, we're able to get the upper limit of our damage detection, which is 99.99% of E. Now, that's nearly perfect. And the reason why is because we are using finite element model. It is a numerical example, and certainly experimental studies are going to be much more of a challenge. I'd like to briefly show you some of our completed experimental studies as proof of concepts. We had a 3.5 by 5 1,200-pound concrete slab, and we induced concrete cracking with a saw, which are the red lines, and we noticed that the damage indication was most notably around those cracked areas and the maximums where they should be. Over on the upper right, we now took a demolition drill and knocked out blocks of the structure, which is about half the depth. So what we have in this red shaded area are lost mass locations, and around that is where we indicated damage from the sensing. It was very nice to see that the noise on the outside was pretty small, except in one location where it's 27%, but that would still reduce the number of areas that the inspector would look at. And at the bottom we have a wood pile. They can lose mass due to insects, they can lose mass due to water, erosion. So we mechanically reduced the area in the center in the red range, and we found out that that had an 85% effect of possibility of the error. And as we leave that area, the noise decreased as we go farther away. And that was a measurement where we had sensors at every 1 foot location along 14 feet of pile. We used the concrete work to evaluate the settings on the genetic algorithm, which include population size, number of generations, crossover function, crossover fraction, and the function tolerance. So thank you, and some of the new contributions that we have are some new damage indices. We considered 3 dimensions, used the genetic algorithm to do a best fit plot, as well as determine the best damage index.